I am Anil Kumar. Welcome to my series on inverse trigonometric functions. I'm going to give you a fresh look on these functions and approach the questions in many different ways so that students worldwide can understand the topic better. You can always visit my website globalmathinstitute.com. The focus here is global learning. I'm going to share with you my experience of last 10 years working with students worldwide. How do they see each topic and how can we help them understand it better? In this introduction to inverse trigonometric functions, we'll discuss what are inverse functions, basic concepts. Then we will see the trigonometric inverse functions one by one. I'll focus in this video on sine, cosine, and tangent. We'll take up the cosecant, secant, and cotangent functions in the next video, and thereafter we'll solve many questions involving compound angles. We'll also discuss how to find the principal values of inverse functions, how to find domain also for these inverse functions. Then we will take examples with some composition of these functions and focus on domain of inverse functions, which could help you solve many examination style questions. So as you can see here, the sine function graph is sketched for you, and clearly sine function has many to one relation since many values are associated with one value, correct? So in that case, we cannot really have inverse as a function for the sine function, likewise for any other trigonometric function. But by restricting the domain, as you have seen here in the other graph, by restricting the domain, we can make it one-to-one onto function and thereby find the inverse of the same. That is going to be our strategy. So let us begin with what these functions are and get the basic concept of some words which are commonly used in reference to inverse functions, right? One of the word which has been always very confusing is injective function, right? Now we are saying that sine function is not an injective function since it fails the horizontal line test. As you have seen here, if I draw a horizontal line as shown here, it intersects the graph at many points. And that means that if I find the inverse of this function, then that will not be a function itself, since many values can yield one result. So it will not be a function, right? So injective functions can be many to one, like a parabola also. Perfect. Sine is also not, and these injective functions cannot have the inverse as a function. That is the key thing. Second definition is surjective functions. Now in surjective function, every element in the codomain should have a preimage. But in sine function, the codomain, rather the range, is only restricted to -1 and 1. So all those elements do not have any preimage. So sine function is not a surjective function. Well, with these two, it can never be a bijective function, right? Since you know, bijective functions are the ones which are both injective and surjective. Perfect. Now you get some basic clue that this is definitely has to be restricted in some way or the other. Now in case of sine, we have to restrict the sine function in both domain and range. So as you can see in the graph, if I restrict it from minus pi by 2 to plus pi by 2, we see that the function is always increasing, right? So in this interval, as you can see here, it is always increasing. Now in this interval, this function is both injective and surjective, and therefore we can say it is a bijective function, one-to-one onto function. So restriction between the domain from minus pi by 2 to pi by 2 and range from 1 minus 1 to 1. That helps to make this a bijective function, right? So our restriction here is from minus pi by 2 to minus 1 and from pi by 2 to 1. So we do have an absolute minimum and absolute maximum value for this, and the function is always increasing. So by this restriction, what have we created? We have created a bijective function. Perfect. And this function can have inverse. So likewise, we are going to restrict domain and range of all the trigonometric functions so that their inverse is a function, right? And then we'll understand in details how to work with them. So let's begin with the sine function itself. So as we were discussing, we're going to restrict the domain and range of the sine function. Domain is restricted to minus pi by 2 to pi by 2 and the range from minus 1 to plus 1. So on this particular graph, I've only shown you a section which we are going to consider in all our examples for inverse of sine function. So the minimum point here is from minus pi by 2 to minus 1, and the maximum point which we are taking from the sine graph is pi by 2, 1. Correct. Now to find its inverse, what can we do? Well, we can actually reflect this on the line y equals to x to get our inverse function. In that case, the points will flip over the line y equals to x. The x and y coordinates will change and so rather swap. And so we get now a maximum on the inverse function, which will be at 1 and the value will be pi by 2. The absolute minimum will be at minus 1 at and the minimum value will be minus pi by 2 as you have seen here in this particular graph. Clear? So that is our principal graph. Well, we could have restricted this domain from minus pi by 2 to pi by 2. We could have taken some other interval also, right? That section of the interval of pi could have been utilized in other places to find the inverse. However, this will be treated as the principal value and most questions will be answered with reference to this. Okay, so what do we have here? We have a function now where the mapping is from minus pi by 2 to pi by 2 to minus 1 and 1 because of the restriction, correct? So f theta can be written as sine theta. You can place a value x to it. Now the inverse of sine will be the angle theta, right? So here are a few examples to consider. Now first, let us see the graph in more details with the help of our coordinate points itself. So the function sine theta equals to x. So the minimum value is at minus pi by 2 given to us as minus 1. At minus pi by 3, the value will be minus square root 3 over 2. And likewise, we have given you key points which are of our interest. Now, based on these key points, we can always calculate the inverse by swapping the values, right? So the y value becomes the x value and the x value becomes the y value. So those can be swapped and you get the values for the inverse function. And then they can be plotted on the graph to get the result which is shown right there. Is that clear to you? Right? So likewise, we have done for some key points within the interval minus pi by 2 to pi by 2. Perfect. You notice that this particular graph of sine theta as well as sine inverse x, both of them are always increasing. And they are in quadrant 4 and in quadrant 1. Do you see that? So, what we notice here that all the values of the inverse function will lie in quadrant 1 and quadrant 4. So minus 1 minus pi by 2 and plus 1 pi by 2 all the values will lie in these two quadrants. So whenever we are given some values, the principal value will lie in either quadrant 1 or in quadrant 4 as shown with this particular diagram. Correct. Now let's take up examples to understand this concept. So the example number 1 here is to find the principal values of some inverse of sine function. Sine inverse square root 2 over 2, sine inverse minus half, sine inverse of pi by 2, sine inverse of minus square root 3 over 2, sine inverse of 0, and sine inverse of 1 is to be evaluated in this example. Now to find the inverse of trigonometric function, it is kind of important to look into our special triangles. So the special triangle right here is this of pi by 4, where the legs are 1 and 1, hypotenuse being square root 2. We'll also see the special triangle, which is pi by 3, pi by 6, pi by 2. Now here the side lengths are 1 and square root 3, hypotenuse being 2. Remember, we are talking about the values, which are from minus 1 minus pi by 2 to plus 1 pi by 2. So those are the expected solutions. And this is the inverse function shown right there. Perfect. So to find inverse, square root 2, if that is involved, we know pi by 4 should be our solution. Correct. So we can actually correlate and get the value. Sine being positive in quadrant 1. So it is going to be the positive pi by 4. For a negative value, which is half in this case, we know the special triangle related to pi by 6 will be the answer. So these triangles give you a visual look and easy solution. So whenever you are attempting questions based on trigonometry, especially the exact values, in that case, sketching these triangles is a good strategy. Well, we know that the values which we are going to give as a result are restricted within minus pi by 2 to pi by 2, and the only value is minus pi by 6. Similarly, now moving away to pi by 2. Well, pi by 2 is what? Pi can be considered as 3.14 approximately divided by 2. This value is greater than 1. So that is beyond the domain of inverse of sine, and therefore this value does not exist. So there could be questions like this. Now similarly, you could do the other three as shown here. Now let's take up the next example, which is based on the domain of the function. So in example 2, we'll find the domain of the function. So I've taken two sine inverse functions, sine inverse 2x minus 5 and sine inverse square root of x minus 2. How do we solve such questions? Here is a very simple strategy. You know that the domain of sine inverse x is within minus 1 and plus 1, both included, right? So we'll begin from there. When I write sine inverse of 2x minus 5, then 2x minus 5 should be within minus 1 and plus 1, both included. Now it is a question of solving inequalities. You can add 5 to all the three terms, cancelling the 5 from the center, and then you can divide by 2. Once you do that, you get your solution that the domain is between 2 and 3, both included. Perfect. Now let's see, how do we solve an inequality involving square root? Now sine inverse of square root of x minus 2. That means square root of x minus 2 should be between minus 1 and plus 1. To solve for it, we know the square root is always positive, right? We know the square root is always positive, so we can write this as greater than equal to 0. So that becomes our lower end. Now we can square all, so squaring will convert that x minus 2 square root 2 to x minus 2. We can add 2 to each term, getting our answer as the domain being between 2 and 3, both included. I hope that is absolutely clear. So these are two types of questions which we'll take up in this particular video. And now let's look into the cosine function itself. Now, as you know, the cosine function is is a function which, again, like sine, repeats, is periodic, right? So it's kind of periodic, as we have seen here. Now, in this particular function, we can do a restriction, which could be from, because this is, you can see, if I draw a horizontal line, in that case, clearly, there are 2 points, more many points, in fact, where the horizontal line is going to cut across the function. And therefore, what we should do, we have to restrict. We restrict in this case from 0 to pi, right? So restricting from 0 to pi helps us get a function which is 1 to 1. And the inverse of this is possible, correct? So that is the domain restricted for cosine function. You can see this function is always decreasing. And if the function has no turning points, you can say that the inverse can be found as a function. Clear? So that is the key. So we have no turning points. So for the cosine function, we are interested in the domain 0 to pi. As shown here, that becomes the domain for the inverse of the function. Okay. So now we are going to restrict the function from 0 to pi, and we know that the range of the function is -1 to 1. To find its inverse, we'll get a function itself. So now the domain becomes -1 to 1, and the range becomes 0 to 5 for us. So here are some values for cosine theta equals to x. Now these values are the standard, exact values which you can always use to sketch the graph. To get the inverse of the function, what are we doing? To get the inverse of the function, we are going to swap the x and y coordinates, and once you do that, then you get the coordinates, which can help you plot the function's graph, inverse function graph, I mean, correct? So that is how you get the inverse function graph. So do it for these values, plot the graph, and see for yourself how does it look like. Perfect. Now that is how we have drawn the graph for the inverse function. As you can see clearly here, it has absolute maximum, right, to begin with, and it ends with 0 as the minimum value, correct? So that is how you could actually graph this particular function, right? So here is the graph for the, which looks like as shown here. Let me highlight it. Okay. So in this particular function, we get a maximum value of minus at -1, pi being the maximum value, and the minimum value will be 0 at 1. Correct. So that becomes the domain from -1 to 1, and the range being from 0 to pi in the case of cosine function. Clear? So that is how we are going to sketch the function and understand it for our discussion in this part of the video. Okay, so let's move on and take examples based on how do we find the principal values for the given inverse functions. So we have 6 questions to answer. Find the principal values of cos inverse square root 2 by 2, cos inverse minus half, cos inverse 2 pi by 6, cos inverse minus square root 3 by 2, cos inverse of 0, and cos inverse of 1. I'd like you to pause the video at this stage, answer these questions, and then look into my suggestions. Now, as we have explained earlier also, it is very important to sketch the special triangles with pi by 4 and with pi by 3, pi by 6, and pi by 2. Now, these two special triangles easily give you most of the values which you can refer to and get the answer. Also, it is good idea to have the graph of the inverse function in view as shown here. So as you can see here, the cos inverse of x, the domain for us is what? So the domain is from -1 to 1, and the range is from 0 to pi, correct? Which is indicated right there. So these are kind of important sketches which help us solve questions based on inverse of the function. And that yields the principal value, correct? Okay, so as we have shown here, all the solutions, remember this part, that 2 pi by 6 is actually greater than 1. So it is not within the domain of cos inverse x, and therefore its answer will be that it does not exist. The rest of the values have been calculated and shown for your reference. Now let's have a look at how do we find the domain of a given inverse function in cosine. We have again two examples. The first one is cos inverse x plus 3, and then a similar one as we did earlier, cos inverse of square root of x minus 2. I would like you to pause the video at this stage, answer this question since you know the concept, and then look into my suggestions. So we know that the cosine value will be having a domain between minus 1 and 1, both included. So x plus 3 should be within minus 1 and plus 1. To solve for this inequality, we'll subtract 3 from all the three terms, getting the result as x between minus 4 and minus 2, both being included. For the square root function, well, I solved for a square function, so let me change this, right? So sorry for the typing error. So this question basically was cos inverse of x squared. Okay. So it becomes a different question. How do we find the inequality involving x squared? Now, important question here is, what is square root of x squared? Remember, it is not x. You will do a mistake if you do that. It is absolute value of x. This is key to understand. Square root of x squared is absolute value of x. Now, let's continue with our solution. So we need to find the domain of cos inverse of x squared. X squared should be between minus 1 and 1. We know x squared is always positive, so we'll make it in between 0 and 1. So square root of x squared is absolute value of x. So when you square root both the sides, you get absolute value of x should be less than equal to 1, and that really means that x value should be within minus 1 and plus 1, both included. So that is how we are going to solve this particular question. I hope the concept is absolutely clear. Now let's talk about the tangent function. Like sine in tangent function, what are we going to do? We are going to restrict our domain from minus pi by 2 to plus pi by 2. In that case, we get our tangent function, which is always increasing without any turning point. So what we did was we restricted the domain from minus pi by 2 to plus pi by 2, and in this domain we observe that the function is always increasing. So this always increasing function will definitely has inverse as a function. Well, you can clearly see that range of tan x is basically tan theta is from minus infinity to plus infinity. So range is all real numbers for the given function tangent theta. Now, if you find the inverse of this function, then domain and range will swap. And so, what do we get? We get the domain of tan function, inverse function, as all real numbers, right? So domain is x belonging to real numbers for the tangent function, right? Tan inverse x. We also write this as arctan, okay? So I'm using this convention at present, arc, and the range for the tangent inverse function will be what? From minus pi by 2 to pi by 2, and this is the principal value which we will be interested in as we move along, correct? So that is about the tangent function. Rest all is very similar to what we learned about the sine function. So we are restricting ourselves to this particular region to solve all the questions. Perfect. To sketch the graph as done before, you can take some standard values for tangent theta, swap them to get the values for the inverse, correct? swap them to get the values for the inverse function and sketching this function will be good practice to begin with. Now you can clearly see that in the function, tangent function has vertical asymptotes. When you find the inverse of the function, these vertical asymptotes get converted to the horizontal asymptotes as shown here. So we have these horizontal asymptotes. So the value of the function will only approach pi by 2 and minus pi by 2, but it will never be there, right? So I should have drawn these with, right, brackets not included. Perfect. That is kind of important to understand. So they are approaching, that becomes the horizontal asymptote. However, the domain can be any real number as shown in the figure. Let's move on and take some test examples based on inverse of tangent function. So to begin with, here is example 5. You need to find the principal values for some inverse tangent functions given here. I would like you to pause the video at this stage, answer this question, and then look into my solutions to check your answers. Again, we are consistently sketching these standard special triangles. They always help you to understand. The figure on the right gives you a reminder that what values we should be expecting in our solution, right? And thereby we have these values, correct? So always the values will be either the positive or the negative theta, which are kind of acute angles, right? So that is what we are interested in. So when we say find the principal value, we mean that theta in radians is what we are interested in. As you can see the solutions right there, that is how we are going to solve this particular question. Remember, the domain for tangent function is all real numbers. Now let's summarize what we have learned so far. So to find inverse functions, we restricted the sine function, cosine function, and the tangent function. The restriction for the sine was between minus pi by 2 to plus pi by 2, right? And for cosine, it was from 0 to pi. For tangent, from minus pi by 2 to plus pi by 2. So this is summarized here. For sine inverse function, the domain is from minus 1 to 1, range being minus pi by 2 to plus pi by 2. Sine inverse function is an increasing function with a minimum value at minus pi by 2 at x equals to minus 1, and the maximum value of pi by 2 at x equals to 1. For the cosecant inverse function, domain is minus 1 to 1, range being 0 to pi. It is a decreasing function with minimum value of 0 at x equals to 1, and the maximum value of pi at x equals to minus 1. It is, as said, decreasing function. Tangent inverse function has a domain of all real numbers, range being from minus pi by 2 to plus pi by 2. They are not included. It is an increasing function which has horizontal asymptotes y equals to minus pi by 2 and y equals to pi by 2. So I hope that summarizes. Now let us combine these functions and then work with the composite functions. So the three examples now which we are going to consider are kind of challenging questions for most of the tests in this topic. So now the question example 6 here is based on the composite function. We are given the function tan inverse of 2 cos 2 sine inverse half. Correct? You need to find the, rather simplify this particular function. Okay, so let's evaluate this function. So we are going to evaluate. Okay, so the second function which we have taken was sine inverse cos tan inverse square root of minus square root 3. So when we have composite functions, we have to work from inside out. That is the key strategy. Perfect. So highlight this key strategy, which is to work from inside out whenever you're working with the composite function. So the inside part for this function is the first one which we are trying to, sine inverse of half. So we need to see what is sine inverse of half. Well, sine inverse of half is pi by 6. So these triangles really help us to understand the value, correct? To begin with, you can always draw these triangles and then confirm your answers. Correct. So what we will do here is, while evaluating, sine inverse of half will be written as pi by 6, right? Now in this expression, it is 2 times, so we'll multiply by 2 and simplify it. So then, what do we get? Well, we get cos of pi by 3. The value of cos of pi by 3 is half, as shown here. So we're going to substitute this by half, and then we get tan inverse of 1. And tan inverse of 1 is pi by 4. Right. So tan inverse of 1 is pi by 4, and therefore the answer in this particular case will be pi by 4. Clear? So that is how we are going to evaluate the inverse of the function. Now let us do the second one, which is sine inverse of cos tan inverse of minus square root 3. So we will begin from inside, which is tan inverse of minus square root 3. So getting into our triangle, that is what we are looking into. The negative sign will make the result also negative, and so we get negative pi by 3. Correct? We know tangent theta is an odd function, and that is what results into this value. Correct. Now, cos is an even function, right? Remember this. So cos is an even function. So we know that cos of minus theta is actually equals to cos theta. And therefore, we from here to here wrote cos of minus pi by 3 as cos of pi by 3, evaluated the value of cos pi by 3 as half. Sine inverse of half gives us pi by 6 as our answer. So the answer here will be pi by 6. So we get pi by 6 for part B and pi by 4 for part A. Correct? Now let's take composite function, rather a complicated function with sine inverse, and we are now trying to find the domain. So the question here is to find the domain of the function sine inverse of 2x divided by x plus 1. Well, strategy to begin with is same. The inverse domain of a sine function is from minus 1 to plus 1, both included. So we'll begin by substituting 2x over x plus 1, right, within minus 1 and plus 1, both included. Remember, x is not equal to minus 1. Since that will make the denominator 0, you can't divide by 0. Now in this particular case, since we have an inequality with rational function to solve, we'll split it into two parts. Correct. And then solve. So the left side is where 2x over x plus 1 is greater than or equal to minus 1, and the right hand side is 2x over x plus 1 less than or equal to 1. Let us solve these inequalities. Let's see the left hand side first. So the left inequality to solve, we are adding 1 on both the sides. We do get a rational function, and then we'll see. Simplify it. We get 3x plus 1 and x plus 1. You can use different methods at this stage to solve this inequality. So one of the common methods is to use an interval table, right? So you can make an interval table. We know that at x equals to minus 1, we have a discontinuity, a vertical asymptote. We need to check around that point. And also, at x equals to minus 1 over 3, we do have another 0. So we have a 0 for x equals to minus 1 over 3, and we have infinity. We'll put a circle here since that minus 1 is never included. And with this table, we will see in which region is this positive. That is the whole idea. So you can take test points in these regions. We have to have a value which is which satisfies this particular equation, right? So let us see. So if you take a test point minus 2 in this interval, and here we take a test point which is minus 1 over, so you can convert to decimal values. For example, this is minus 0.3, you can say minus 0.4, right? So you could do that. And then let's say if I divide by 2, so that will give us half. 0.5 will be a good value to take, minus 0.5. And on the right side, you can consider a value, for example, 0. And see, if I substitute minus 2 here, do I get a value which is positive. So minus 2 will give me negative numerator and negative denominator. They will cancel and we do get a positive value. If I put a value which is in between minus 1 over 3 and minus 1, in that particular case, we get a negative value. But if I put a value which is greater than minus 1 over 3, for example 0, I get in this case a positive value. So clearly, the answer could be within these intervals where x is less than minus 1 or x is greater than equal to minus 1 over 3. You cannot include minus 1 in your solution. Now, let us also find the result from the right hand side. Okay, so here we clearly get one result on a number line, and that result is that the value of x could be on the left side of minus 1 or on the right side of minus 1 over 3, and this being included, filled in circle. Correct. Now let's get into the other half where we are trying to find the solution for 2x over x plus 1 less than equal to 1. We'll subtract 1 as we have done, and then we do get a rational function. Solving rational inequalities is by interval table, for example. Correct. We were looking for the values which are less than or equal to 0. Of course, minus 1 cannot be included in this particular case, right? So, greater than, okay? So, minus 1 cannot be included. So, what we notice from here that the solution is from minus 1 to 1. So, we get a solution which is from minus 1 to, let's say, 1, right? So this value is 1 from us. So this net solution will be the region which is overlapping. The 1 is included. Perfect. Minus 1 is not included. So region which is overlapping is between minus 1 over 3 to 1. And that becomes the solution. Is that clear to you? So combine these two. The overlapping interval is the solution, and that is how you're going to solve it. Here is the last example, which is to find the domain of the function which is cos inverse of 1 plus x squared over 2x. I'd like you to take this as your test question, right? Take it as a test question. You can now pause the video, answer this question, and then look into my suggestions. Now again, we'll solve the inequality where 1 plus x squared over 2x should be between minus 1 and 1. Remember, x cannot be equal to 0 in this particular case. So we'll always split rational function inequalities like this into two parts and then solve them individually. So one part is this, which is talking about greater than minus 1, and the other part when it is less than plus 1. So these are being solved on two sides. On the left hand side, minus 1 is less than equal to 1 plus x squared. We'll add 1 on both the sides, simplify, factor. We get x plus 1 whole square in the numerator and 2x in the denominator. This value should always be positive. In that case, the x value should be greater than 0. And we know x cannot be equal to minus 1. Well, when it is greater than 0, that question doesn't arise. Okay, so x equals to minus 1 also helps to find this particular solution since it gives you a 0. So we're looking for a solution where it is equal to 0 or greater than 0. Correct. So that becomes the solution from the left hand side. On the right hand side, what do we get? We want 1 plus x squared over 2x to be less than equal to minus 1. When we subtract minus 1, we get 1 plus x squared minus 2x in the numerator, which can be factored as x minus 1 whole square. And this number should be always less than equal to 0. The numerator is positive, and this can be 0 only if the denominator is negative. So x value has to be less than 0, where x is equal to 0 is also a solution, right? So we have two solutions here. X equals to 1 gives me a 0. In the previous one, x equals to minus 1 gives me a 0. So those two values are definitely the solutions, but otherwise we get the intervals which are not matching, right? So in the two solutions, what are we getting? Well, this is x is greater than 0. So if that is 0 for us, one solution is saying x is greater than 0. The other one is saying that x is, let me use a different ink here, the x is less than 0, right? So nothing matches as far as these two are concerned. However, we do have 2 points, x equals to minus 1, correct? So we have a point which is x equals to minus 1 and at minus 1 and at x equals to 1. Now at these 2 points, we see that the value is satisfying both the conditions. And so that becomes the solution for this particular equation, right? So that is within our interval. Now here is a particular graph which shows you the portion. So these are the 2 points shown on the graph which represents the solution of this particular domain of the function x inverse 1 plus x square over 2x. So only for these two values we have the solution. I hope that really works. So feel free. So with this, we end our session on the introduction to the trigonometric functions. I hope it makes sense. Feel free to write your comment, share your views. If you like to subscribe to my videos, that'd be great. You can also register on Global Math Institute to learn more. Thanks for your time and all the best.